Good morning all, my name is Santhosh Kumar, Assistant Professor, Institute of Aeronautical Engineering. My subject is Computer Architecture. Today I am discussing about problem solving on arithmetic operation. So in the arithmetic operation, especially we are going for arithmetic pipeline. So in the arithmetic pipeline, we are going to go for the arithmetic operations of pipeline. So pipelining is a technique of decomposing a sequential process into sub operations, with each sub process being executed in a special dedicated segment that operates concurrently with all other segments. Each segment performs partial processing dictated by the way of the task is partitioned. The result obtained from the computation in each segment is transferred to the next segment in the pipeline. So, arithmetic operations majorly we are performing pipeline arithmetic operation. So, here today we are discussing arithmetic operation with pipeline method or pipeline process. So, before going to this arithmetic operation in the pipeline process, what is pipeline? So, pipeline is a technique of decomposing a sequential process into sub-operations, with each sub-process being executed in a special dedicated segment that operates concurrently with all other segments. Each segment performs partial processing dictated by the way the task is partitioned. The result obtained from the computation in each segment is transferred to the next segment in the pipeline. So, pipeline is nothing but it is a process. So, it is a technique to process the arithmetic operations. So, suppose we have to perform A into B plus C. So, first we have to go for A into B, after that perform C. So, what we have to perform first? So, first A into B, it is a segment 1, C segment 2, segment 1, segment 2. Okay. So, how many segments we need? A into B is a one segment and we have to take C, it is another segment, and addition of segment 1 and segment 2 is another segment. Okay. So, A into B plus C is a one operation, but we are dividing to the sub operations. Why? Because A into B is one operation and we have to take the value of C is another operation, and A into B, after the getting the result of A into B, what is the result? This result plus C we have to add. So these are called sub operations. The operation, how many we are dividing to the sub operations, that is called segments. So any of the operation we are dividing to the segments. These segments are called sub operations. Each segment performs partial processing dictated by the way the task is partitioned, and the result obtained from the computation in each segment is transferred to the next segment in the pipeline. So, what is the segment? A into B is a one segment. So, what is the result of this one? S1 equal to A into B. So, what is the result of A into B? And next, S2 equal to C. Next, S3 equal to A into B plus C. So, what is the result of A into B and what is the value of C? Then we have to add A into B plus C. That is in the segment 3. So, that is a partial dictated by the process of the task in the computation, with each segment transferred to the next segment in the pipeline. The final result is obtained after the data have passed through all segments. Each segment consists of an input register followed by an combination circuit. A clock is applied to all registers after enough time has elapsed to perform all segment activity. The information flows through the pipeline one step at a time. So, we are going to perform sub operation of A into B plus example C into D. So, what is the result of A into B? What is the result of C into D? So, this result plus this result. So, this is called, I am taking as suppose R1 and this is I am taking R2. So, what is the final result? R1 plus R2. Segment 1 plus segment 2, that is called segment 3. Segment 3 equal to segment 1 plus segment 2. So what is the final result of segment? Final segment value, that is a final result is obtained after the data have passed through all segments. Each segment consists of an input register followed by an combination circuit, and a clock is applied to all registers after enough time has elapsed to perform all the segment activities. The information flows through the pipeline one step at a time. Suppose I am taking y equal to a into b plus c into d plus e. So how many segments? A into b is segment 1, segment 2, segment 3. So segment 1, this value, what is the result of A into B? That is a segment 1. C into D result, what is that? That is a segment 2. And what is the value we are giving? That is a segment 3. Next, what is the segment 4? So segment 4 equal to segment 1 plus segment 2. Segment 1 plus segment 2. A into B value, A into B value plus C into D value. That is a segment 2. So I got A into B value plus C into D. Suppose here I am taking A into B values, I am taking X, and C into value I am taking Y. So it is X and it is Y. So what is the X plus Y? That is the segment 4. Next, segment 4 is completed. X plus Y, I got the value. So this is the X plus Y, I got this value. That is subject. So z equal to x plus y. So now what about the e? So suppose here I am taking w equal to, what is the value? X plus y equal to z. So w equal to, this is completely z plus e value. So that is a w value. So it is a w segment is a, it is a w I am taking as a segment 5. So segment 5 equal to, what is the x plus y value here now? Z. So z plus, that means segment 4 value plus e value, that means segment 3 value. So segment 5 equal to segment 3 plus segment 4, that is a segment 5. So it is a w equal to segment 3 plus segment 4. It is a total of a into b plus c into d plus e. Example, perform a into b plus c. Here I am taking ai, bi, ci. Why? Because I have to take multiple values of a. So that is for I equal to 1, 2, 3, 4, 5, 6, 7 using pipeline method. So we have to perform the arithmetic operation, that is a into b plus c. So what is the technique? So we are using here pipeline method. So pipeline method is nothing but we are dividing into the sub operations, or we are dividing into the segments. So what is the first segment? Here I am taking ai into bi plus ci. So now what is the segment 1 here? Segment 1 is that much. I am taking R1 equal to AI and R2 equal to BI. So A into B, that is the R3. R3 tends to R1 into R2. R1 is tends to A register value and BA register value. It is R1 and is a R2. What is R3 means? R1 into R2. And this is I am taking as a R4. So R4 tends to CI value. So now what I have to do? R1 plus R2, A into B value, R1 into R2. What is the value now? R3. So it is the R3 plus, what is the CI equal to R4. So R5 equal to R3 plus R4. So how many segments I need? So 3 segments I need. That means 3 sub operations we need to perform. So segment 1 R1 to AI, R2 to BA. So 2 registers here. But total how many variables are there? Total 3 variables. So for 3 variables we need 3 registers. 3 registers means what I have to take? R1, R2, R3. So R1, R2 and R3. So R3 to R1, R1 is R2. Here I'm taking, in place of CA, I'm taking R4. So total 3 registers I'm taking. So addition of 2 registers, I'm taking another register. So like this. So A into B means register 1 multiply with register 2. What I need? Register 3. So this result will be stored in register 3. CA already occupying one register. So this value of register plus this value of register, we are adding both together. So what is the value? That is a final register. That is a segment 3. Example of pipeline processing. Here in the previous I am taking A equal to, I am taking calling one register A R1. For B1 I am taking, or B8 I am taking R2. So multiplication. What is the value here? A into B. So I need a multiplier. Multiplier means R1 into R2. That means also called AI into BI. So I am taking multiplier. So this multiplication value, what is the result of R1 and R2? It will be stored in R3. So R3 is nothing but the R3 is nothing but the multiplication of R1 and R2. So that is the R3. So R3 equal to R1 into R2. So R3 equal to R1 into R2. So that is completed. Next, CA. I am taking only CA. Why? Because A into B is one register. Only CA. There is no other than is there. So I am taking CA. I am taking this is a R4. So this resultant value plus this resultant value, that is called, I need adder. Plus means adder. So I'm taking adder. So what is adder now? Here R3. What is the result of R3? R1 into R2 plus CA value is R4. So R3 plus R4. So R3 plus R4 will be stored in R5. So R5 equal to already this one R3 plus R4. That is the R5 value, like this. So sub operation, the total sub operations are how many I need? Total sub operations are how many I need with 3 sub operations, 3 segments. So first segment, second segment, and third segment. First segment 1, 2, and it is a third segment. A into B, segment 2 equal to C, and segment 3 equal to A into B plus C. So content of registers of pipeline. How many segments I need? 3 segments we need. So I'm taking clock pulse 1 to 9. So 1 to 9 I'm taking as a clock pulse. So segment R1 or R1 R2. Already we know that R1 tends to A1, R2 to B2. Already defined R1 equal to A1 and R2 equal to B1. So A1 into B1, R1 into R2. So here segment 2, what will happen now? So in the segment 1, we are defining R1 equal to A1 and R2 equal to A1 and R2 equal to B1. In the segment, in the second clock pulse, R1 equal to A2, B2, A3, B3. Like this, I am taking as a I equal to 7. So for I equal to 7, 1 to 7. So that is the reason we are taking as a clock pulse as 7 segments now. So like this, A1, B1, A2, B2, A3, B3, A4, B4, A5, B5, A6, B6, A7, B7. Segment 2. So in the segment 2, what will happening now? A1 and B1 is multiplied and the C1 should be ready to add. So in the segment 2, A1 into B1 and C1 is ready. Next A2 into B2, C2 is ready to add with this resultant value. A3 into B3, so on A7 into B7. In the segment 3, what will happen? Segment 1, we are defined. Segment 2, C1 is defined. In the segment 3, the resultant, that means R3 and R4 should be added. So here A into B is nothing but a R2, that is R3, and equal to R4. So R3 plus R4, that is a R5. So A1 into B1 plus C1, like this, A7 into B7 plus C7. So like this, I am taking as a R7, that is a R3, R4, R3 into R4, like this. So A into B, what is A into B now value? R3. It is a R4. So R5 equal to A into B value, that means R3 plus R4. R3 plus R4. So any operation that can be decomposed into a sequence of sub operations of about the same complexity can be implemented by a pipeline processor. The technique is sufficient for those applications that need to repeat the same task many times with the different sets of data. A task is the total operation performed going through all segments of a pipeline. The general structure of a four-segment pipeline is as shown. So any operation, supposing here we are taking A into B plus C, any operation that can be decomposed into a sequence of sub operations. Okay, it is one, it is another, and it is a total. So segment one, segment two, and what is the domain? Segment three. So the technique is efficient for those applications that need to repeat the same task many times with the different sets of data. A task is the total operation performed going through all segments of a pipeline. The general structure of a four-segment pipeline is as shown below. So we are taking the general structure of four segment. Presently we discussed three segment, but next we are going for the four-segment pipeline. So segment 1 with suitable register as R1, segment 2 with R2, segment 3 with R3, and segment 4 with R4. So this is a four segment pipeline. Previously we discussed only three segment. Now I am taking as a four segments. How many clock pulses we need? Four clock pulses. Why? Because four segments we need four clock pulses. Okay. So S1, R1, S2, R2, S3, R3, S4, R4. So total four segments and four clock pulses. So four segments with four clock pulses. In that, next arithmetic pipeline. Already we discussed pipeline. So pipelines are two times arithmetic. Pipelines are two types: arithmetic pipeline, instruction pipeline. First, we will discuss arithmetic pipeline. Arithmetic pipeline units are usually found in very high-speed computers. Arithmetic pipelines are constructed for simple fixed point and floating point arithmetic operations. To understand the concepts of arithmetic pipeline in a more convenient way, let us consider an example of pipeline built for floating point addition and subtraction. So one example we'll discuss now. So what is the arithmetic pipeline? Suppose A into B plus C into D. Is it arithmetic operation? Yes. Why? Because we are multiplying here and we are adding together. So arithmetic operations means we are going for the arithmetic operations like addition, subtraction, multiplication, division, increment, decrement, like these operations. So here it is one example of arithmetic operation. So the pipeline is suitable for arithmetic operations. That is the arithmetic pipeline. But here arithmetic pipeline is constructed with two types. That is a simple fixed and floating point, integer values and floating point values. To understand the concepts of arithmetic pipeline, let us we are going for one example to understand the floating point addition and subtraction. So actually floating point means 1.126, 0.128, 2.25, 2.25, 13, like this. Okay, so we are calling as a 128, 256, we are as an integer values. These are the floating point values. So here I am taking floating point arithmetic operation or fixed point operations. So these are the fixed and these are the floating point values. Example 2. Perform the following floating point add operation using pipeline. Here they are giving one example: x equal to a into 2 power a, y equal to b into 2 power b. So we are asking that floating point addition and subtraction, or floating point adder operation. Here is adder means we have to go for the addition. Using pipeline. Answer: the two normalized floating point binary numbers are these are the floating point numbers. So these are the floating point numbers. A into B are the two fractional numbers, that is 1.256 or 2.678, like this. Okay, and 2 power A and 2 power B, that is are the exponents. So it is a Montesa and exponent. So these are called Montesa and these are called exponents. So A and B are the Montesa, small a and B are called the exponents. So we have to take one example to perform the floating point adder using pipeline method. So how we are, what are the rules for to combine, or what are the rules to perform the floating point adder? The combined operation of floating point addition and subtraction is divided into four segments. Each segment contains the corresponding sub-operations to perform in the given pipeline. The sub-operations that are shown in the four segments. So in this diagram, x equal to, in this example, x equal to a into 2 power a, y equal to b into 2 power b. So we have to add these things. Okay, these are the floating point with Montesa and exponents are there. So what are the conditions? Means what are the sub operations to perform? So here we have to take four segments. So why I'm taking four segments, we'll discuss now. To combine the operation of floating point addition and subtraction, divided into four segments. Each segment contains the corresponding sub operations to be performed in the given pipeline. The sub operations that are shown in the four segment. Compare the exponent of subtraction, align the Montesa, add or subtract the Montesa, normalize the result. First compare the exponents. First compare the exponents. So compare the exponents. Compare exponents. Align the Montesa. I have to align, add or subtract to the Montesa. So add or subtract means balance the Montesa. Next, normalize the result. So these are we go into the normal form. Normal form to solve the addition. The following block diagram represents the sub-operations performed in each segment. In the block diagram, in the flowchart, we have to discuss what we have to do step by step. It is a Montesa and these are the exponents. Already we know that a into 2 power a. So what is a Montesa here? It is a Montesa. It is an exponent. So I am taking here exponent small a and small b. Already in this diagram is there. Small a and small b are the exponents, and Montesa is a capital A and capital B. So we have to go for the we are exponents. What is the first condition? Compare the exponents by subtraction. Comparing means we have to go for the one register to compare operation. Or exponents. Compare the two values or two exponents, and compare exponents by subtraction. I'm taking one register. First I'm creating a register to compare the two exponents. Here first segment, what will happen? Compare exponents by subtraction. Using the subtraction method, we are comparing A and B. And next I am taking one result, or what is the result? After the comparison of this one, what is the result? It will be stored. Result will store in register A, and choose the exponent. So I was compared. Suppose a equal to 3, b equal to 4. So are you taking both are 3 or both are 4? So which you are finalized. That is one thing. And choose the exponent. And after the choose the exponent in the segment 2, we have to choose the exponent. So which you are choose? A equal to 3, b equal to 4. So both are taking 3 or both are taking 4. You have to finalize. That is a choose the exponent. That is in the segment 2. In the segment 3, what is the final result? Are you taking 3 or are you taking 4? Suppose I am taking 3. These 3 you should be storing here. If I am taking 4, you have to store this one in the register R. Adjust exponent. So we have to adjusting the exponents, and it will be stored in register R. After the Montesa. So we have to take the Montesa. What is the rule here? Align the Montesa. So we are aligning. I am taking one register to aligning the A and B. After aligning the Montesa, it will be stored in R. So add or subtract the Montesa. So if you are going for the aligning the Montesa, what you have to do? Add or subtract. Here in the question they are asking add. So we are going for the add operation. And after the addition, that will be stored in R, and normalize the result. It will be stored in R. So A equal to 2.124 into 10 power 4. B equal to 1.256 into 10 cube. So we have to first what will happening. So here 4 and here 3. We had to balance. Here 2.1, here also 1.2. So there is no change. Suppose here B got 11.2, but here 2.2. So after one digit, it will be floating. Here after two digit. So A equal to 2.1. That is a one digit of floating. But here B equal to 11.2. That means two digit. So we have to balance these. A and B we have to balance. Montesa we have to balance, and exponent has to balance. So how we are balancing? Compare exponents by subtraction. The exponents are compared by subtracting them to the determining their different. The larger exponent is chosen as the exponent of the result. The difference of the exponents, that is 3 minus 2 equal to 1, determines how many times the Montesa associated with the smaller component must be shifted to the right. X equal to 0.9504 into 10 cube, y equal to 0.82 into 10 square. So it is a 10 square and it is a 10 cube. So we have to balance. Here 0.8, here 0.9. So no, there is no change. Why? Because 0.8, 0.9. So these are balanced. So what we have to do now? The difference of the exponents, that is a 3 minus 2 equal to 1. It determines how many times the Monte is associated with the smaller exponents must be shifted to the right side. So okay, we will discuss now. And align the Montesa. The Montesa assigned with the smaller exponent is shifted according to the difference of exponents determined in segment. X equal to 0.9504 into 10 cube, y equal to 0.08 into 10 cube. So it is a 10 cube and a 10 square. So that is the reason I'm changed it to, it is changed to 10 cube. It is a 10 cube now, it is 10 cube. So how it is changed, 10 square is changed to 10 cube means I'm taking one digit right left side, 0.08. Here 0.8, here 0.08. So x equal to 0.95 and y equal to 0.08 into 10 cube. So here align the Montesa, here compare the exponents, and exponents compared here 2, here 3, like this. Here and align the Montesas. Next, add Montesa. The two Montesas are added into that. Z equal to x plus y. Here x a y. Z equal to x plus y. Here z equal to what is x equal? 0.9504 into 10 cube plus 0.08 200 into 10 cube. So these exponents are balanced. Now we have to balance this one. So x plus y equal to. So what is the value now? 1.0. So 1.0324 into 10 cube. So these are balanced. And 1.03 here 0.9, 0.08, 0.08, 0.9, 1.0. So is it balanced? No. Why? Because here it is a 0 point, here it is a 0 point, but here it is 1 point. So we have to balance 0.103 24 into 10 power 4. Why? Because here in the input 0.9, here also 0.9. So definitely we have to get the output as 0.9. So 1.0 means I'm shifted to right. That is 0.10324 into 10 power 4. So we are normalized the result. So after the normalizing the result, z equal to 0.1324 into 10 power 4. Example 3. Using arithmetic pipeline, perform the following addition and subtraction of floating points on a pipeline unit. Consider two normalized floating point binary numbers as inputs in the floating point adder pipeline. They are defined as p equal to u into 2 per u and q equal to v into 2 per v. It is one example. So p equal to u into 2 per u, q equal to v into 2 per v. So we have to take two variables. And what is the value of p? 0.9800 into 10 square. Here 0.7900 into 10 power 1. So what is the first step? We are going for the two normalized floating point binary. So these are floating point. Yes, these are the normalized floating point numbers. What is first one? Here u and v are the exponents. Capital U and v are the Montesa exponents. Montesa. So the process of floating point addition and subtraction is divided into four parts. Each segment of the pipeline is dedicated to a specific sub operation. These sub operations include, so this process of floating addition and subtraction divided into four parts. So we have to take the four sub operations or four segments. So what are the each one we will discuss. First one, comparing the exponents using subtraction. So compare the exponent. What is exponent value here? 2 and here. Okay. So comparing with 2 and 1. Align the Montesa. So Montesa here 0.9, here also 0.7. So there is nothing will happen. And adding or subtracting the Montesa. If it is not balanced, we have to add or subtract. If balanced means no need. After the addition and subtraction, normal is the result. That is the fourth condition. So four sub operations we need. Four sub operations can follow for the pipeline, arithmetic operation. Based on the difference of expense calculated in the first segment, the amount is associated with smaller exponent is moved also. So p equal to 0. Here p equal to 0.9800 into 10 square. Next q equal to 0.787900 into 10 power 1. So we have to first balance the this one. So we have converted to 10 square. So what will happen now? P equal to 0.98 into 10 square. So I have to 0.07900 into 10 square. So 0.07, 0.98, 0. So I have to 10 plus 1. So we have to increase the 10 square means it will be aligned to right side. So we have to decrease means we have to go for left like this. So 0.07900. So is it balanced? Yes. Then what is our question? Using the arithmetic pipeline, perform the following addition and subtraction. So first I have to go for the p plus q. So 0.9 plus 0.07. So what is the addition value now? P is 1.0590 into 10 square. So in the question you can understand it is a 0.9, it is a 0 point, but here 1 point. Is it balanced? No. The Mondays is not balanced. We have to convert to, we shifted to right. 0.10590 into 10 cube. 0.10 into 10 cube. So it is a 5. Why? Because 0.9, 0.0. Here also 0 point. So Monte is balanced, exponents are balanced, adding subtraction is completed, addition is completed. So next we are normalizing the result. So adding the Montes are step by step. The third segment involves the two Montes are equal to p plus q, 1.0590 into 10 square. Okay. After then the process of comparing the exponents by subtraction. The first steps involves calculating the difference between the exponents by subtracting them. The larger exponent is selected as the exponent of the result. The difference in exponent equal to 2 minus 1 equal to 1 indicates the number of times the Montesa associated with the smaller exponents needs to be shifted to the right. So what is the process to compare? Means we are comparing with Montesa and exponent. The first step involves calculating the difference between the exponent by subtracting, and the larger exponent is selected as the exponent of the result. The difference in the exponent equal to 2 minus 1 equal to 1 indicates the number of times Montes are associated with the smaller exponent needs to be shifted to the right. And we are understanding the normalize the result. After the normalizing result, 0.1059 into 10 cube. So it is a block diagram below for sub operations. So how many sub operations you performed? First, exponents are we have to balance the exponents. We have to balance the Montesa. After then, addition. After then, again normalizing the result. So we need three segments. So it is a block diagram or segments. How many we need? So it is for exponent and it is for Montesa. Exponents two are there and Montesas are the two are there. So we are comparing the exponent. Definitely we need one register. We have to Montesas two. Definitely we need one register to compare, and comparing the exponents by subtraction in the segment 1. So segment 1 is happening, compare the exponents. So is it any difference? We are aligning the mantissa. If there is no difference means we are not aligning, and the resultant should be stored in R, and in the segment 2 choose the exponent. So suppose one is 10 cube, another one is 10 square. So what do you finalized? Are you finalizing 10 cube or are you finalizing 10 square? Suppose here 2 into 10 cube, here 5 into 10 square. Which one you are chosen? 10 square or 10 cube? What is the finalized? That will be in the segment 3, and adjust the exponent, and what is the adjusted value, it will be stored in R. In the Montesa segment 1, comparing the exponents by subtraction, is there any difference? We are aligning the Montesa with one register, and add or subtracting the u plus v like this, and what is the result, addition or subtraction, it will be stored in R. After the result, we are again normalizing with the exponents and Montesa, and the resultant value stored in R. These are the references. So today we discussed what is a pipelining in a composition technique. So pipelining is a technique to decomposing a sequential process into sub operations, with each process being executed in a special dedicated segment. There are two types of pipelines are there. That is a arithmetic pipeline and instruction pipeline. So it is about the arithmetic pipeline with one example, A into B plus C. So I'm taking R1, R2, and resultant and addition of this one I'm taking R3, and it is to R4. Total I need R4, R5 equal to R3 plus R4. So it is a arithmetic pipeline. What are the conditions for simple fixed point, floating point arithmetic operation? To understand the concept of arithmetic pipeline in a more convenient. So example 2 I'm taking, perform the floating point addition subtraction, x equal to capital A into 2 power A, y equal to B into 2 power B. So we have to first take the Montesa and exponent and balance in that one. So compare the exponent, align the Montesa, and add or subtract, and normalize the result. So four sub operations we need to perform. The following is a block diagram of sub operations, and we are comparing the first exponents. We are comparing 3 and 2 comparing, and aligning the Montesa, here 0.9, here 0.0. So both are equal now, and add the Montesa. So x plus y, two variables we are adding. After the addition, again we are balancing the exponent and Montesa. So using arithmetic pipeline, perform the following addition with the floating point numbers. P equal to U into 2 for U, Q equal to V into 2 for V. With suitable examples I'm taking. Here exponent to 1. So we have to modify the exponents. We have to balance and exponents and multiplies and perform the addition and subtraction. Then normalize the result. It is a process and it is a flow chart to arithmetic pipeline. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.